Okay, thank you. Well, thank you for the invitation. I'm sorry that I can't be there in person and that I wasn't able to join the earlier part of the session. It's a couple of hours earlier in the UK, so I've only just finished dropping off children at school. But it's great to be able to give this talk, and I hope to have some discussion and join in with the rest of the session later on. My talk is going to be on the topic of learning from density functional theory, from first principles calculations, to produce effective Hamiltonians and then use them to produce accurate and transferable materials models. So it's an alternative to the idea of machine learning potentials that you might have heard about elsewhere or earlier on. Just to put this in context a little bit, in my group in Warwick, what we're interested in doing is modeling what I call chemomechanical processes. So that's processes where there's some chemistry going on, something like breaking bonds at the tip of a fracture, as shown over here, or friction at the atomic scale. This is an atomic force microscope tip in contact with a rough surface. But at the same time, there's also long-range stress field. So obviously in fracture, there's a balance between breaking bonds and relieving elastic energy ahead of a crack. And so in order to make an accurate model of these kind of systems, we need to cover a good description both of long-range mechanics and local chemistry. Same thing is true in oxides and for plasticity processes in metals, and in particular for things like advanced materials, like new steels, where we need to understand the concerted action of stress in chemistry through corrosion, cracking, or embrittlement. So that's my motivation. That's the kind of problems I like to try to solve. These are quite challenging because we need at the same time quantum mechanical description to describe bond breaking, but also very, very large model systems, which are very hard to do with traditional quantum mechanical techniques. Oh, wrong direction. And so this is a typical picture of the hierarchy of materials modeling techniques that one might apply to these things. To have sufficient predictive accuracy to develop new materials or to understand processes, typically we need to be working at roughly the density functional theory level. And unfortunately, that limits us to a few hundred atoms. These numbers are quite old now, so perhaps we can push up to 1,000, but still quite limited in system size. And in particular, the timescale is really quite limited. We can only model for a few picoseconds at this level of accuracy. And a lot of work has been done to try to push up the accessible length and timescales by using slightly more approximate techniques. For example, type binding, I'll talk a bit about that later on, or empirical molecular dynamics calculations. What I want to talk about first of all is something I've been involved in for quite a few years, which is to concurrently couple techniques. So to use a small region of the system treated with high precision and embed that within the rest of the system described classically with a more approximate technique. And this has some advantages, but it also has some limitations. So I want to show one or two examples to present what the limitations of this approach are, and then we'll see how we can address it with the new method that I propose in the title of the presentation. So this is an example of this concurrent technique. We have a fracture system here that we'd like to model. This is silicon on the 111 cleavage plane, and we're interested in understanding crack propagation. In order to capture the stress relaxation, we need 10 to the 5 or 10 to the 6 atoms in the system so that the boundaries aren't placed too close to the tip of the propagating crack. So that's the kind of scale we're looking at here, 10 nanometers or 100 angstrom scale bar. So this is around 1,000 angstrom, 100 nanometers system size overall. And the blue atoms here we treat with density functional theory, but the rest of the system is treated with an approximate method. So the advantage of the particular scheme that I've developed, the learn on the fly scheme, is that we can move the quantum mechanical region during a calculation. And you can see that we end up with a good description of the fracture process, and we capture quantum mechanical details like this is a Panday 2x1 reconstruction of the surface, rather than just the plain hexagons that you see with a simple model. The quantum mechanics describes the alternation of pentagons and heptagons associated with pi bonding and delocalization of electrons along this fracture surface. So we can make predictions with that. The problem is we're limited to the timescales that we can access with density functional theory. The overall clock is determined by the speed at which we can compute this molecular dynamics simulation. So we're still limited to a few picoseconds at most. We can address that a little bit if we're interested in rare events by, instead of calculating dynamical simulations like I've shown here, computing minimum energy paths and energy barriers for activated processes. So here's an example of that. This is dislocation glide in tungsten, relevant for radiation shields for fusion reactors. Here we see the core of a dislocation moving from one stable site to the next one, and then the associated energy barrier for that process, which we can compute using this multi-scale embedding scheme. So here we have the dislocation moving along the path. We can see the stable minimum energy path in this map here. And what I'm showing in this figure on the right is that if we use our multi-scale method with the same density functional theory that's been used by other people, then we can essentially reproduce the energy barrier for dislocation glide. And we do a much better job than using the simple classical model on its own, shown here in brown, which massively underestimates the energy barrier and hence would get the mobility of the dislocations and the plasticity response completely wrong in this material. But again, we're limited here. We can only treat small regions of the system with high precision. Here we're just treating a few atoms near to the core of a dislocation. We can perhaps look at interaction with impurities, etc. We also don't have any access to electronic structure or electronic properties. So this is not a first principles method. It's a way of understanding material science or mechanics using some first principles information, but we don't get access to electronic properties. That's partly what motivates the new technique I'll be introducing later in the talk. One recent work that I wanted to show that's relevant for diamond and semiconductor industry, perhaps, is some work that my PhD student, James Brixey, who's just finishing his thesis now, has done, where he's been using the same technique in diamond to look at interaction between fracture and nitrogen impurities. So here we have a pristine piece of diamond. We model it in the same way with a small part of the system described with density functional theory, and the rest of the system described with a simple empirical model, in this case a Tursoff potential. And the plane fracture without any impurities proceeds exactly as in the silicon case I showed you earlier on. Bonds break one by one, and fracture proceeds perfectly brittle fashion, step by step. If we introduce a nitrogen impurity, a substitutional impurity, ahead of the crack tip, so the black atom down here, we've changed a carbon for a nitrogen. We find quite interestingly that this can interact with the propagating crack and cause it to take a step up in the cleavage direction, so in this 111 direction here, an atomic step up. And every time you encounter a defect, we anticipate the same thing will happen. So we can make a prediction from these simulations about what we would expect to observe experimentally, and that's that if there's an increased concentration of nitrogen defects in the material, we should expect a rougher and rougher fracture surface with more surface features. And that's exactly what's observed in experiments carried out by Tom Cowie and Andy Jardine in Cambridge. If you have a specimen which is essentially defect-free, so you've grown it with deposition, epitaxial deposition, CVD, you have a low concentration of defects and not too many ridges on the fracture surface. If you have a higher concentration of nitrogen defects, you see many more of these small triangles that we think correspond to initiation of ridges of defects in the fracture surface. And we can actually make a simple model that's inspired by the calculations that we've done that just says, if you initiate a ridge at each of these defect sites, what kind of surface microstructure would you expect? And you can see it matches up pretty well with what we see in the experiment. So we've got some quite good quantitative evidence that this mechanism can explain these observations in the fracture surface. But thinking about the limitations of the technique, again, we just did a couple of trajectories here. They were very expensive. It took James most of his PhD to get to this result because we go at the speed of the DFT calculations. And it feels a bit wasteful to do that. If you watch this simulation at the top here, bonds break one after the other. Everything looks rather repetitive and similar. There's no real need to evaluate very expensive calculations every single time step. We should try to learn from that and build some kind of machine learning model which could reproduce these results much more quickly. So that's, of course, something that people have been doing for quite a long time now, constructing hierarchical models where we take density functional theory and we build some kind of surrogate for it, either using an old style empirical potential, right, like the ones that I've mentioned, a Tursoff potential or a Stillage-Weber potential, using ideas that go back to the 80s, modified, inspired by chemical intuition to construct these potentials, or a more modern approach is to use a non-parametric representation of the potential and to inform that from calculations done with, for example, density functional theory. I'm not going to say too much about that. I think you're hearing about it in other talks from Jörg Behler, for example, earlier on, and also in the session later on. But I just want to mention a couple of recent things that I've done that are perhaps interesting for people interested in this area. So I'm not an original developer of the Gaussian approximation potential technique. That was developed by Gabelchani and Albert Barta-Pate in particular, but I've helped to contribute recently to some of its recent enhancements. So I'll just say a little bit about that before moving on to the main topic. And that is a technique where we express the potential energy in a system as a combination of comparisons between the atom that we'd like to make a prediction for and a set of reference atoms that we contain in the database. And then we have some weights here that we determine through a fitting process, essentially. But the basic idea is we compare every atom we'd like to make a prediction for with a set of reference atoms. And we have to do that comparison in a way that obeys the physical invariance in the system. So if you move your system around, the energy shouldn't change. If you swap two atoms that have the same chemical species, the energy shouldn't change. And if you rotate the system, the energy shouldn't change either. And that's the basic idea that is embodied in this SOAP descriptor that some of you may have come across, the smooth overlap of atomic positions that was developed by Albert and Gabor quite a few years ago now. The idea is that you construct a density of atoms by placing a Gaussian on all of the neighbors around an atom, modified by some smooth cutoff function. But essentially, we add up a series of Gaussians to give a representation of the density. That already gives you permutational invariance because we're doing a sum here. So we sum over atoms, we sum over Gaussians, we get a density field that now doesn't change if we change the order in which we do that sum. But we haven't yet got the rotational invariance. We also get the translational invariance, by the way, by working with relative differences here with displacement vectors rather than absolute positions. To get the rotational invariance, it's a bit more tricky. The idea is that we compare one density with another by taking the first density, multiplying it by the second after applying a rotation R, and then we integrate over all the rotations. That's the idea. So we smear one density representation through another over all of the rotations. The sum alpha here is over chemical species. I'll say a little bit more about that later on because that has led to one of the limitations and challenges in the approach to date. So the straightforward approach is just to compare all chemical species with all other chemical species. And then there's a formula essentially for how you get these weights. It's just linear algebra, and I won't go into the details, but it's related to Gaussian process regression, if you've heard or come across that before. One key thing to emphasize is that this sum here isn't over everything in our database, it's over a small subset that we choose to be representative. So we might learn from 100,000 pieces of DFT information, and we use just 10,000 sparse points to represent them. And that's an important thing to emphasize because there's often a misconception that the cost of this model grows as the size of the database grows. That's not true. We effectively choose some size for our basis, and that's a modeling approximation that we can make. Okay, this has been very successful. You've probably seen some of the recent applications. There's a very nice review that's been put together by Volker Deringer and others if you're interested in applications of Gaussian regression, Gaussian process regression for materials modeling. I'd recommend having a look at that review. But there are some challenges and some limitations. I want to talk about two of them. One is this idea of how to model many chemical species. So this sum over alpha here can get really problematic. The way that we do this in practice, we don't do this integral analytically. We convert this density into an expansion, a series expansion that we truncate at some point, and the length of that series expansion scales quadratically with the number of chemical species in the system. So if you go from 2 species, let's say silicon carbide, to 3 species, we want to include hydrogen as well, silicon, carbon, and hydrogen, we go from a cost of 2 squared, 4, proportional to 4, to a cost of 3 squared, which is 9. So more than double the cost by adding another chemical species. And it gets worse and worse as you go higher and higher. So if you want to model modern materials like high entropy alloys or organic molecules, this becomes really problematic. The second challenge is related. It's what happens if you want to use very large training sets. And the challenge there is that this linear algebra then gets very difficult to do. This matrix here, KMN, is the big guy. That involves comparing each of your reference environments, your sparse points, with your entire training sets, which, as I said, could be hundreds of thousands or even millions of points. And it becomes impossible to fit this into memory if you have very large training sets. So I'll describe some work that we've done recently to address that. Most of the other steps in here are not too big. This one here is a small matrix, so it's really just this KMN and its transpose here that become problematic. Okay, so the first thing is, the first challenge that I mentioned is many chemical species. The way that we've addressed this is some work by a postdoc working with me, James Darby, who has spent some time in Gavel's group in Cambridge and is now with me in Warwick, and he's come up with the idea of generalizing the representation that we use, so that it doesn't just compare all the chemical elements. It has a part here which is element sensitive, and then we multiply it by something else which is agnostic to the element. So we've dropped the species label here, we've dropped the alpha. Here we just compare the density. So silicon and carbon look the same as one another, they're just atoms. And by choosing these powers, mu and nu, if I go back for a minute, you'll recall in the original, there's just a single power here. We typically set this to 2. Then by spreading the representation between the sensitive part and the agnostic part, we can compress the size of the representation. The original representation, the original SOAP, as I mentioned, scales quadratically with the number of species and also quadratically with the size of the radial basis set, how well we describe things in the radial direction. We can compress first by going one step to the left, so we keep the same amount of radial precision, but we drop to linear scaling with a number of chemical species. That can make quite a big difference. The way I've represented that here is by saying, rather than comparing all the different species, so here we've got a central atom we're interested in, it's got 2 neighbors, one is a blue species and one is a red species, and here we fully resolve all that species information. What we do here is slightly blur things, so we see only one of the species at a time. So we have a blue species, and then this part here is agnostic, and here we've got the red one, and this part is blurred. We can go one step further and also compress the radial information. So the dashed circle here represents projection onto the unit sphere. Rather than representing all of the atoms actually at the distances that they actually occur, we could bring them in and project them onto a sphere of radius 1. And again, if we do that for one neighbor at a time, then together we've got a reasonably good overall representation. So James has implemented this and tried it out. We tried it on a high entropy alloy data set that came from Kai Nordlund's group, and it looks very promising. We're quite excited about the prospects here. So I'll just talk you through these results. This is the original gap approach here, the red curve. You can see its accuracy is coming down, but it saturates at some point. And actually, we couldn't go any further than this because we ran out of memory because of the high cost of evaluating these descriptors. So even on a very high memory, 2 terabytes or more compute node, we couldn't go very much larger in precision. Whereas with the compressed representations, particularly the green one, which seems to be a good compromise, as we push up the size of the basis, we get more and more improvement in accuracy, and the cost is much reduced. So we get higher accuracy for lower cost in this case, which is very good. Okay, I mentioned also the second challenge of using large data sets. What we've done there, and again, a postdoc who's working with me, very good computational scientist, Sasha Kloen, working with me and Albert Bartok-Partey here at Warwick, has taken a big linear algebra problem and split it up into pieces, essentially. It sounds straightforward, but it's been quite challenging to do in practice. We're trying to solve this linear system here, which is essentially a least squares problem that we solve by QR factorization. And what we do is distribute this matrix A into pieces and then use a library called Scale APAC to do that, to solve that linear system in parallel. This is also looking very encouraging and working very well. It scales very well up to a few thousand cores. And it seems that we get the best balance if we use a mixture of MPI, so that's separate processes, and also multi-threading. So the first number here is the number of MPI processes. The second is the number of OpenMP threads. And in the middle here, doesn't seem to matter too much what you do. If you use entirely MPI with no threads, then you start to saturate after a while. You can't divide the matrix into small enough pieces that you don't become dominated by communication. And you also, because you have some overhead from each process, you also have a lot of memory requirement. But with these intermediate choices, you can go to very large core counts, and that means you can drop the time that it takes to fit one of these models from a few days to a few minutes. But more importantly, you can use very much larger databases because you're not limited to the memory that you've got on a single compute node. You can use your entire cluster. You can use thousands of cores and the memory that's available on all of them. So we're excited about this work. There's a preprint on the archive if you want to read more about this already. But now I'll move on to the main topic of the talk in the last 10, 15 minutes, which is not to jump over the type binding idea and to come up with some representation of the density function of area information that still includes electrons, that doesn't go all the way to just ball and stick type models that we use in molecular dynamics, but which is much faster to compute and is driven by data. So let's talk a bit about how this works. This has been published just earlier this year in MPJ Computational Materials. You can find all the details there, but I'll try to explain the idea. For this, we used a local orbital DFT code. You could do this with a plane wave code like CASTEP, but we haven't done that in this case. If you wanted to use a plane wave code, you'd first have to go through a step where you projected the results of your DFT calculation onto a local orbital basis set through linearization, for example. But we haven't done that here. We've used a code that uses local orbitals, the FHIM's code. And so we solve the DFT problem on a set of training structures, and we get Hamiltonian and overlap matrices out, and then we form a database of these matrices together with the structures that led to them. And then I think I'll go through what's shown on the right first of all, and then come back to these equations on the middle a little bit later on. This is a representation of the Hamiltonian matrix that you get. We're looking at aluminium. We've used a simple SPD basis set. So we have 14 orbitals for each of our atoms. The green blocks here are the on-site blocks, so that's interactions between two different orbitals sitting on the same atom, and the purple blocks represent off-site interactions, so interactions between different atoms. But both of them have the same structure inside. There's interaction between the different types of orbitals within each atom. And what we've done is we've noted that the way that these matrix elements transform has what's called an equivariant structure. So that means that if you rotate the atomic system, then the Hamiltonian rotates in this way. So that's your original matrix, and that depends on your atomic positions. If we apply a transformation Q, then the way that the matrix transforms is given by the Wigner-D matrices of the appropriate angular momentum acting on the block of the matrix. And you can do that for each of these subblocks separately using appropriate YLMs. Yes? There's a question? No, maybe just somebody not on mute. So the way that we do this is we represent these blocks using something called the atomic cluster expansion that was proposed by Ralph Droutz 2 or 3 years ago. And we can do that in a similar way for the on-site and the off-site parts of the matrix. The on-site part is simple. It's just like an interatomic potential. We have a spherical environment around the atoms, and we can represent that with the basis. The off-site part is a little bit more tricky, and we need to do that using a cylindrical environment around atoms. So we use a cylindrical environment that describes a bond, essentially. We then do something equivalent to what I showed you with SOAP earlier on, and that we average over the symmetry group, and that gives us, in the end, linear models for the Hamiltonian and the overlap. So we compute some basis functions, multiply by some coefficients, and we get a prediction for the Hamiltonian blocks on-site, off-site. We do the same thing for the overlap matrix, just for simplicity. So once we've got that, if we want to solve a problem, we take our structure, we go and predict the Hamiltonian elements. I'm not going to go into the details of the basis construction. I'm happy to discuss that in the questions or or you can have a look at the paper for full details. And then we just need some coefficients. We get them by doing a simple least squares fit. It's actually a regularized least squares fit, but it's very simple. It's a linear model, so it's easy to fit, and there's no difficult training of neural networks or anything anywhere in this process. It's all quite straightforward. How does it work? Well, first of all, we look at the accuracy of the matrix elements. Both the on-site elements and the off-site elements converge well as we increase the size of our basis set. So we increase the maximum polynomial degree that we use in our representations. The error on our training set goes down. The dashed lines are the error on the test set. They all go down as well nicely, but we start to see some overfitting for high polynomial degrees. So we restrict ourselves from going any higher. Things get worse if we move to higher body order, higher correlation order. We include more atoms in the description of the environment. So we're actually stuck with this order 1 representation. Correlation order 1 means we've got 2 atoms in the bond, 1 atom in the environment. So overall, there are 3 bodies involved, which is why I've called it body order of 3. We tried this out on aluminium. We can see that as we increase the size of our basis set, we can get systematic convergence of the electronic structure. So this is the band structure predicted without having to do the DFT calculation. We do still have to do a diagonalization, so it still costs, we still have to diagonalize the matrix, it's still cubic scaling, but we skip the SEF and many other parts of the DFT calculation. Here's the density of states converging in a similar way as we increase the size of the basis set. That's FCC. We also looked at BCC aluminium. We didn't explicitly include either of these ground state structures in the data set, so these are quite good tests. We trained on molecular dynamics samples where the atoms were displaced away from equilibrium, and then we tried it out on these ground state structures. The density of states, again, is converging nicely, certainly up to the Fermi level, and even a few electron volts above is quite well represented with this approximate model. Okay, I think I'm a little bit short on time, so I'll just show the last couple of results, which are that by tuning the basis, we can get a good prediction for the ground band structure and the density of states. And we can also do some more challenging tests. We fitted only on FCC and BCC, so that's the 2 ends of this path here. Now we're looking at what's called the Bain path, so that's where we transform from FCC to BCC by stretching the unit cell. And we're seeing how well our model performs in between those 2 extremes. We find the error is actually smaller everywhere along that path in between FCC and BCC, and both the error in the density of states, the error in the bands is well controlled. We did a more challenging test. We only had trained our model on bulk configurations, but we used it to predict the electronic structure near a vacancy. So for the nearest neighbors of a vacancy, we looked at the projected density of states there, and it works surprisingly well, despite not explicitly having seen any defects anywhere in the training. So green here is the original FCC density of states without any defects. We predicted the density of states for a vacancy in red, and then we used we predicted it in blue, and we also checked it with DFT directly in red. And you can see up to the Fermi level, it's pretty well reproduced. Okay, I'll finish there by thanking everyone who's been involved, particularly in the equivariant Hamiltonian modeling project that I described. In my group at Warwick, that's postdocs Adam McSloy and Bert Konat, in collaboration with the group of Reinhard Maurer in chemistry and the group of Christoph Ortner at UBC in Vancouver, particularly the first author, Liwei Zhang, who's a postdoc who was here at Warwick and then has moved to UBC recently, Geneviève Dusson from CNRS in France, and Gautam Anand, who was a postdoc with me in Warwick and is now an assistant professor at the Indian Institute of Science and Technology in Shibpur. The paper is out, so you can find all the details. We've made the data available and the code, and there's a tutorial example if you want to have a go at looking at how to use it yourself. Thanks very much for your attention, and I'll be happy to try to answer any questions.
Hi, thank you for giving me the opportunity to talk about my research.
Thank you. Okay, that's great. Thank you.